All right, so we have a expected value problem with a game. It doesn't really matter if it's a game or a business application. In any case, you take the possible values and multiply each one by the chance of getting that value. So if there's a 50% chance of winning $20 would be your value, and that would get multiplied by zero point 0.5. And then you'd have the other possible values. Of course, you want your total possibilities to add up to 1 to be a valid probability distribution. You can use that as a double check. All the different probabilities should add up to 1. But what you do then is you take each value times its probability, add those up, and that's your expected value. So let's say that W, actually, let me get a brush. There we go. There we go. W is amount of winnings per game, per time you play the game. Now, he could lose money. That would be just a negative value of W. So let's take a look at his expected value of W. So we need the different values he could get. So it said he wins an amount equal to the value of the card if an odd number is drawn. So that would be like a 1, which would be a 1/10 chance, or $3 should also be a 1/10 chance. You'd really have a 1/10 chance at any of these. Now you might wonder why the probabilities aren't going up here. Well, whether you draw a 1 or a 7 or a 9, it's all just one of the 10 cards have that amount attached to it, right? You're no more likely to draw a 9 than you are a 1, or less likely for that matter. So those are our odd numbers, drawing a 1, a 3, a 5, a 7, and a 9. And then we have to subtract, or actually add a negative value rather, of $6 every time we get an even. So what's the chance of getting an even? Well, there's 10 cards, and how many are even? The 2, 4, 6, 8, and 10. 5 of those 10, and I'll keep it with 5, 10. 1/2 would be fine. So these are all the possible values. In the parentheses here, you're going to see all the possible payoffs for a single game. And then right beside it is the chance of getting that payoff. So if we add all these values here, I'm going to just add the numerators since we have a common denominator on each one. So 1 plus 9 is 10, 3 plus 7 is 10, and 5. 25 there across the top, minus 30 would give me -5 over 10. If what I did there mental math, don't worry about that at all. You can type all of this into a calculator. And the point is it'll give you -5/10. So let's simplify that. How we might normally write it would be -50 cents, right? So each time, on average. Now, the funny thing is, notice it's impossible for him to lose 50 cents on a single game, right? Because that's not even one of our possible payouts. They're all either positive 1, 3, 5, 7, 9 or a -6. So what does this actually mean? It means if he plays the game many, many times, on average, he's going to lose 50 cents per time. Now he might play it 3 times and win $27. That'd be the max. Or he might play it 3 times and lose $18, or something in between. But if you take many, many, many times and then divide by the number of times he played, on average, he's going to come out -50 cents. It's not a good idea for him to play this game a lot, right? And in fact, that's the answer to the second question. What can he expect to lose after playing the game many times? And it does tell us that each time is a fresh game. It's not like we pull a card and then that one's no longer there. And it says he can expect to lose $0.5. Now, you might wonder, why is that not a negative number there? It's because of this word lose. Although, here's a perfect case. If you would put in -0.5 here, especially if you had this part A right, I would look at that and say, okay, that was just a misinterpretation of the English, the question there. the way they worded it, but the mathematics, you clearly understood that, and I would override and give you full credit. So if you do ever have something like that where you knew what was going on, it was just the way that it was interpreted in the software was a little bit off, then just let me know, and I'm happy to give those points back. Yeah, so by the way, it doesn't ask us in this question, but what if you would play the game, let's say, 200 times? What's our best guess for his total winnings? Well, if on average he's losing 50 cents a game and he plays 200 times, that would be an expected loss of $100, right? So we would have 200 times negative 0.50, which is why the more times he plays, the more we're going to expect that he loses. It could be a little bit less or more than that, but on average, that's what we would see.